Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to talk on module X-ray diffraction part 1 under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to see about the continuous spectrum of X-rays. Then we'll study what is a characteristic spectrum and how the characteristic spectrum is originated. Next, we'll study how a diffraction occurs using X-rays, that is, what is actually the X-ray diffraction. And in the end, we'll study in detail and we'll derive the Bragg's law. Before going into the detail, let's have a brief introduction about X-rays. X-rays are discovered by German physicist Rontgen in 1895. The nature of these rays was completely unknown at that time. Hence, they were named as X-rays. X-rays are invisible, travels in straight lines, and affect the photographic film in the same way as light. They have more penetration power than light and can thus easily pass through the human body, wood, metals, and other opaque objects. Radiography was started long back to study the internal structure of opaque objects even before the understanding of nature of X-rays was developed. In 1912, the phenomena of X-ray diffraction by crystals was discovered, which proved the wave nature of X-rays and provided a new method for investigating the fine structure of matter. Radiography is considered to be one of the most important tools, having a wide range of applications, but it can resolve the sizes of the order of 10 to the power minus 7 millimeter. On the other hand, diffraction is an indirect method which is capable of revealing the details of internal structure of the order of 10 raised to the power minus 7 millimeter. Thus, in this module, X-ray diffraction is studied. The continuous spectrum of X-rays. X-rays are produced when an electrically charged particle, such as electrons having a sufficient kinetic energy, rapidly deaccelerates. The radiation is produced in an X-ray tube which contains a source of electrons and two metal electrodes. The high voltage maintained across these electrodes of the order of 10 kilovolt rapidly draws the electrons to the anode or target, where they strike with a very high velocity. This results in the production of X-rays at the point of impact, which radiate in all directions. If E is the charge on the electron and V is the voltage across the electrodes, then the kinetic energy of the electrons on impact on target is given by the equation E into V equals to half mv square, where m is the mass of an electron and v is its velocity before impact. Most of the kinetic energy of electrons is converted into heat and less than 1% is transformed into X-rays. Upon analysis of the rays coming from the target, it is found that the rays consist of a mixture of different wavelengths and the variation of intensity with wavelength depends on the tube voltage. Figure 1 shows the X-ray spectrum of molybdenum at different tube voltages. It can be observed that for a given tube voltage, the intensity of X-rays is 0 up to a certain wavelength called the short wavelength limit, denoted by lambda SWL. It increases rapidly up to a maximum and then decreases with no sharp limit on the long wavelength side. When the tube voltage is increased, the intensity of all wavelengths increases, but the short wavelength limit and the position of maximum shift to shorter wavelengths. This is because with increase in tube voltage, the number of photons produced per second as well as the average energy per photon both increases. The radiation represented in the curves is called polychromatic, continuous or white radiation since it is similar to white light. That is, it is made up of several wavelengths. White radiation is also called as Bremsstrahlung or braking radiation as it is caused by the deceleration of electrons. The continuous spectrum of X-rays results due to the rapid deceleration of electrons hitting the target since any decelerated charge emits energy. Electrons are decelerated in different ways. Some of them lose their complete energy in one impact and some lose fraction of their kinetic energy in each impact. Photons of maximum energy or minimum wavelength are produced when the electrons are stopped in one impact so that they transfer all their energy. In the equation form, EV is equal to h into nu max. That is, lambda minimum can be written as C divided by nu max, which is equals to hc by EV, which in turn gives 12.40 into 10 raised to the power 3 divided by V. Let's call this as equation 2. The area under the curve resulting from X-ray spectrum gives the total X-ray energy emitted per second. The total X-ray energy per second also depends on the atomic number Z of the target and on the tube current I. The current I is the measure of electrons striking the target per second and is given by I, that is the current in continuous spectrum, equals to A into I into Z into V to the power M, where A is the constant of proportionality, M is a constant with a value of about 2. Heavy metals like tungsten are preferred as target material when large amounts of white radiation is desired. It is important to mention that the material of the target affects the intensity but not the wavelength distribution of the continuous spectrum. So figure 1 shows the X-ray spectrum of molybdenum at different tube voltages. Now let us discuss about the characteristic spectrum. When the voltage on an X-ray tube is raised above a certain critical value, which is a characteristic of the target material, sharp intensity maxima appear at certain wavelengths superimposed on the continuous spectrum. Since the peaks are very narrow and the wavelengths are characteristic of the target material used, they are called the characteristic lines. These lines fall into several sets referred to as K, L, M, N, etc. in order of their increasing wavelength. All the lines together form the characteristic spectrum of the metal used as a target. Now let us see what is the origin of the characteristic spectrum. As discussed, the continuous spectrum results from the rapid deceleration of electrons after striking the target, whereas the characteristic spectrum originates from the atoms of target material. In order to understand this, consider an atom having a nucleus surrounded by electrons in various shells. The shells are designated as K, L, M and so on, corresponding to the value of principal quantum number n is equals to 1, 2, 3 and so on. If any of the electrons bombarding the target has sufficient kinetic energy, it can knock an electron out of the K shell, leaving the atom in an excited state and high energy state. One of the outer electrons immediately falls into the K shell vacancy, release energy and again comes back in normal state. The emitted energy is in the form of a radiation of particular wavelength and is in fact characteristic K radiation. The K shell vacancy may be filled by an electron lying in any of the outer shells, giving rise to a series of K lines. Line result from filling of electron from L shell and line result from the filling of electron from M shell. Since it is most probable for a L shell electron to fill the K shell vacancy in comparison to M shell electron, therefore the line is stronger than line L. Similarly, L characteristic lines originate when L vacancy is filled by its outer shell electrons. The electron transition in an atom are shown in figure 2. Wk is the work required in order to knock out the K electron. Then the kinetic energy of the bombarding electrons should be necessarily equals to half mv square equals to Wk. Therefore, the characteristic spectrum originates only when the tube voltage is above some critical voltage. Since L shell electron is relatively farther from the nucleus as compared to the K shell electron, therefore L excitation energy is less than K and K characteristic spectrum is always accompanied with L, M, etc. radiation. The longer wavelength lines are easily absorbed and thus only the K lines are useful in X-ray diffraction. There are several lines in the K set, of which the strongest ones are K alpha 1, K alpha 2 and K beta 1. K alpha 1 corresponds to 0.709 Armstrong of wavelength, K alpha 2 corresponds to 0.71 Armstrong and K beta 1 corresponds to 0.632 Armstrong. The alpha 1 and alpha 2 components have wavelengths so close together that they cannot resolve as separate lines. If resolved, they are called the K alpha doublet, and if not resolved, simply the K alpha line. Similarly, K beta 1 is simply referred to as K beta line. K alpha 1 is twice as strong as K alpha 2. In general, the intensity ratio of K alpha 1 to K beta 1 depends on the atomic number of target. The intensity of any characteristic line measured above the continuous spectrum depends both on the tube current I and the amount by which the applied voltage V exceeds the critical excitation voltage for that line. For a K line, the intensity is approximately given by I equals to Bi into V minus Vk to the power n, where B is a proportionality constant, Vk is the excitation voltage and n is a constant with a value of about 1.5. The existence of the strong, sharp K alpha line is highly useful for X-ray diffraction as it is used as the monochromatic radiation for most of the diffraction experiments. Figure 2 given here shows the electronic transition in an atom. Now let us see what is actually the X-ray diffraction. The phenomena of X-ray diffraction basically is an interaction between X-rays and the geometry of crystals. For many years, crystallographers had accumulated knowledge about crystals, chiefly by measurement of interfacial angles, chemical analysis, and determination of physical properties, and there was a little knowledge of interior structure. Von Laue proposed that if crystals are made up of regularly spaced atoms, which might act as scattering centers for X-rays, and if X-rays are electromagnetic waves of wavelength about equal to the interatomic distance in crystals, then it should be possible to diffract X-rays by means of crystals. Followed by this, various experiments were conducted to test this hypothesis. Finally, in 1912, the two English physicists W.H. Bragg and W.L. Bragg analyzed the Laue's experiment and successfully expressed the necessary condition for diffraction in a simple form known as the Bragg's law, after the name of the physicist who proposed it. Now let's discuss the most important Bragg's law. Consider a section of the crystal where the atoms are arranged on a set of parallel planes A, B, C, D, normal to the plane of the paper and spaced a distance d apart. Assume that a beam of perfectly parallel, perfectly monochromatic X-rays of wavelength lambda is incident on this crystal at an angle theta called the Bragg angle. Theta is the angle measured between the incident beam and the particular crystal planes under consideration. Our aim is to find out whether this incident beam of X-rays will be diffracted by the crystal, and if so, under what conditions. Diffraction is essentially a scattering phenomena, and a diffracted beam may thus be defined as a beam composed of a large number of scattered rays mutually reinforcing one another. X-rays are scattered by atoms in all directions, and in certain directions the scattered beams will be completely in phase, that is, they interfere constructively, giving rise to diffraction effect. Consider rays 1 and 1a in the incident beam that strikes K and P in the first plane of the atoms and are scattered in all directions as shown in figure 3. Scattered beams are completely in phase only for the directions 1' and 1a' because the path difference between the rays 1k 1' and 1ap 1a' is equal to qk minus pr equals to pk cos theta minus pk into cos theta equals to 0. Similarly, the rays scattered by all atoms in the first plane in a direction parallel to 1' are in phase and add their contribution to the diffracted beam. This will be true for all planes separately. Now, we need to find out the condition for constructive interference of rays scattered by atoms in different planes. Consider rays 1 and 2, which are scattered by atoms K and L of the lattice. The path difference between rays 1k 1' and 2l2' is ml plus ln equals to d sine theta plus d sine theta equals to 2d sine theta. Let's call this as equation number 4. Scattered rays 1' and 2' will be completely in phase, that is, they interfere constructively if this path difference is equal to integral multiple of wavelength lambda, that is, n lambda equals to 2d sine theta. Let's call this equation as equation 5. Now theta equals to sine inverse n lambda divided by 2d. Let's call this as equation number 6. This relation was formulated by W.L. Bragg and is known as Bragg's law. The relation gives the necessary condition for the diffraction to take place. N refers to the order of diffraction. For fixed values of lambda and d, the diffraction may take place at several angles of incidence theta 1, theta 2, theta 3 corresponding to the values of n is equals to 1, 2, 3. In all other directions of space, the scattered beams are out of phase, leading to destructive interference. For same order and interplanar spacing, angle theta decreases as wavelength decreases. Thus, glancing angles are used to study diffraction using gamma rays. So given here figure 3 shows the diffraction of X-rays by crystal. Since angle of incidence is equal to the angle of reflection, the diffraction of X-rays by crystals may be considered as similar to the reflection of visible lights by mirrors. Therefore, the planes of atoms acting as mirrors which reflect the X-rays. However, diffraction and reflection differ fundamentally in three aspects. The diffracted beam from a crystal is built up of rays scattered by all atoms of the crystal which lie in the path of incident beam, whereas the reflection of visible light takes place in a thin layer from the surface only. The diffraction of X-rays takes place only at certain angle of incidence which satisfies the Bragg's law, whereas the reflection of visible light can take place at any angle of incidence. Then thirdly, the intensity of reflected light by a good mirror is almost 100%, whereas the intensity of diffracted X-ray beam is generally very small compared to that of incident beam. Then the next two important geometrical facts related to Bragg's law are as follows. The incident beam normal to the diffraction plane and the diffraction beam are coplanar. Secondly, the angle between the diffracted beam and the transmitted beam is always 2 theta. This angle is known as diffraction angle and it is the angle which is measured experimentally. Since sin theta cannot be greater than unity, therefore we can obtain from Bragg's law n lambda divided by 2d equals to sin theta less than 1. That is, n lambda is less than 2d. Let's call this as equation 7. This implies that diffraction occurs only when the wavelength of wave motion is of the same order of magnitude as the repeat distance between scattering centers. For diffraction, the smallest value of n equal to 1 as n equals to 0 corresponds to the beam diffracted in the same direction as incident beam which cannot be observed. Therefore, the condition of diffraction at an angle 2 theta is lambda less than 2d. Since d is of the order of 3 angstrom or less, therefore lambda cannot exceed about 6 angstrom. So visible light cannot be used for crystal diffraction. That is, for visible light, lambda is approximately equals to 10 raised to the power minus 7 meter. If lambda is very small, specialized equipment is required to measure the diffraction angles. Bragg's law may be expressed in the form lambda equals to 2d sine theta divided by n. Let's call it as equation 8. Since the coefficient of lambda is unity, therefore, a reflection of any order can be considered as a first order reflection from planes, which may be real or fictitious, spaced at a distance 1 by n of the previous spacing, that is d prime equals to d by n. So lambda equals to 2d prime sine theta, and this is the equation number 9. So students, let's now summarize what we have learned in this module. First of all, we studied about the continuous spectrum of X-rays. Then we studied about the characteristic spectrum and what is the origin of this characteristic spectrum. Then next, we studied in detail that actually what is X-ray diffraction. Then in that, we studied how the diffraction from X-rays can be done, who proposed that model, who were the scientists who gave that hypothesis, and so on. Then in the end, we studied about the Bragg's law proposed by the two physicists W.L. Bragg and W.H. Bragg, which actually gave the mathematical form of X-ray diffraction and gave the conditions which are really important for X-ray diffraction to occur. Thank you.